Peter. All right, welcome everyone. Today, the first thing that we're going to be covering is going to be binary search versus, or excuse me, linear search versus binary search. We're going to be covering this over the next couple of hours, and it's going to take us straight into our retro, which is going to be happening at 11 o'clock Central. Now, when it comes to binary search or linear search, actually, we'll start from there. Linear search is a pretty simple concept. Linear search is a concept in which we start from the very left-hand side of some sort of iterable object. Now, an iterable object could be either a string or what else in Python? What else is an iterable object?
List.
Yeah, we have our list as well. We have our, oh, I don't know what's going on with my TLDR here. We have our string or our list, which we can iterate through to be able to grab some sort of answer. This is our iterable object that we can go work through. Now, if we're doing something like linear search, all we're doing in linear search is we're searching from the very left-hand side and hopping over each individual index. Now, we could do this with either alphabetical numbers, or excuse me, with alphabetical characters. Let me go ahead and refresh this here because it is acting weird. All right, we could either do this with string or with a list. And we could do this with alphabetical or numerical characters, where we're iterating through each index of a list. Now, let's say that our list, or let's say our input list, is equal to a list of range 101. And we were looking for the index of the number 99. So inside of this list, we're looking for the index of the number 99. How many times would I have to iterate through a list to be able to find the index of the number 99 if I was implementing some sort of linear search, where I start at the very first index and move on one index at a time?
99?
Yeah, 99 times. Let's go ahead and take a look at that. Let's implement this linear search. We'll go ahead and say linear search. Linear search will take in some sort of list, and it's going to return an integer for the index. And then we'll say for IDX in range input list, or excuse me, len lst
We
if,
need,
oh, go
sorry,
ahead.
do we need to pass in the target as well?
Oh, good catch. Yeah, we also need to make sure that we're tracking the target. So there we're passing the target, which is an integer. We're looking through the list. We're then asking if each index of the list is equal to the target. And if so, we'll go ahead and simply return the IDX. Otherwise, once we iterate through the entire list, we'll return something like -1 to let us know that it doesn't exist. And for the time being, let's go ahead and print IDX to make sure we're keeping track of all the iterations that we had to look through. Let's call this function. Let's say linear search. Put this within a print statement and say that what we're looking for is the input list and the target. When we execute this, we can see a large number, saying, hey, this iterated through this list all the way until index 99. And at index 99, we finally returned the input of 99. Now, this would change if I go ahead and do something like 1 for the very first start character. Now we see that we can receive 98. And that's because remember the 1 is inclusive and 101 is exclusive. So this would create a list of 1 to 800. All right, so that's linear search, which is something that we've put into practical application a couple of times. We're simply just iterating through a list, finding one independent index, and returning that index. Does anyone have any questions regarding linear search? All right, we're not going to go into big O yet and how to determine that factor. TL draw seems to be acting up today for some reason. So let me go ahead and try to figure out what's going on here. All right. So here we have a list of integers. Now, in this list of integers, I can go ahead and take a look, try to find one specific index that matches our target. Now, when I take a look and try to find one specific index that matches our target, I'm going to be starting from the left-hand side and working myself over the right-hand side, checking one index at a time. Now, the problem that we encountered right now is if I was looking for something like the number 98 or the number 99, I would have to iterate through this list 98 times to be able to find my target. Although it is O of n, meaning linear, we looked through or iterated through our input field one time. It's not as efficient as it can be. Instead, what we're going to do is we're going to take our linear search or iterable object, and we're going to break it down to where we're searching for partial input. We are determining whether we're going to be looking to the left or right-hand side, making our iterable object as such. So that instead of looking through our entirety of our list, we're only looking through half of our list at a time. Oh, man. Not sure what's going on with TL Draw. I apologize, everyone, but it seems to keep breaking down for some reason. All right. Now, is there any mortarmen that are present here? Or any forward observers? No? No love for the infantry community? All right. Well, better luck next year. All right.
I was in reconnaissance scout a little bit.
Well, that's pretty close, right? I mean, I'm sure you did some call for fire calls. Inside of call for
Hmm.
fire, there's the concept of bracketing. That's the same thing that applies here to our binary search. Our binary search, it's essentially determining which portion of the search it is that we're looking for. Jesus Christ. All right, I'm not going to utilize steel draw. It's not working out for me very well. All right, so let's take.
That shit.
Oh, go ahead, Akina.
Never mind. Not Mike.
All right, so here we're going to go ahead and create our binary search. Where binary search still takes in our list that we're going to iterate through and some sort of target that we're going to be iterating through. And it will still return the integer of index. Now, how does binary search work? Well, what we're going to determine is going to be the left, right, and middle. Right, so we're going to say left. That's going to be equal to the left-hand side of the array. So that's going to be our 0. We're going to say right is equal to the length of the list minus 1. And then we're going to implement our middle, where the middle is right minus left. All right. So as of now, what we've done is we've implemented some sort of pointer objects. We said, hey, we have our right, or excuse me, our left. We are looking at our right. And we also have the ability to take a look at a middle. Now remember, all three of these are in objects. Oh, and I see a hand go up. Go ahead, Michael.
In this case, would middle just be the same as right? Or would you need to like divide it by 2 or something?
What do you mean by that? Why would I have to divide it by
Right,
two?
let's say the number's
Mathematically,
100. Yeah, right is 100, left is 0. 100
Oh,
minus 0 be
I see, because we're getting 0. Perfect.
yeah, for
Yeah.
mathematically for middle, you add them together, divide by how many you added together. So for this, it'd be 2. So add them together, divide by 2.
Yep. Thank you so much. So we would add them together and then do some sort of floor division, divide by 2. That's my mistake on the math behind that. Right? So we would add right plus left, which in this case is 0 plus the length of the list. And then we would do floor division by 2 to make sure that we get that actual middle index. All right, great catch. Great. So now we have our array. Now, how do we determine how we're going to be iterating or moving this array around? Because again, the factor that we want is we want to determine if our array is too big. We want to make sure that we look through a specific number of information and reset our left and rights along with our middle to continuously take a look. All right. So what we're going to do here is we're going to start a while loop. We'll say while left is less than or equal to right, the following is going to be conducted. And we'll ask if list middle is equal to the target, what we're going to do is we'll simply return our middle. Elif list middle is greater than the target. So in this case, the middle portion is greater than the target. So let's say 10 is greater than the target, like we see in this visual example. Then what we want to do is we want to reset our right to be equal to middle. All right. And we'll leave our left alone. Finally, we can say Aleph or list middle is less than the target, which if I were to draw a visual representation of this, what it would look like is as such. And give me a second and I'll get to all those questions here shortly. All right, so this will be the visual representation in the case that the list middle is less than the target. In this case, we would reassign left to be equal to middle. Now then comes the question, well, why is middle outside of the loop? It shouldn't be outside of the loop. Middle should be continuously reassigned, while left is less than or equal to right. All right, Daniel, go ahead.
Oh, that was the thing that I was gonna add was like that you have to reset your middle every time.
Perfect. All right, any other questions? At the end of this loop, if none of this returns a statement, or if this statement at any point becomes false and it breaks out of my while loop, well, then in that case, I would want to return -1. Now, to break it down, let's say I was looking through a list of integers, and let's change this up a little bit, where we have our range of 1 to 20, where every single time we step by 5. And let's go ahead and just simply print our input list. Here we see 1, 6, 11, and 16, which isn't exactly what we want it to be. Let me go ahead and change this here. I'm going to change this to 30. And I'm going to change this to 0. All right, and now we get 0, 5, 10, 15, 20, and 25. Oof. Let me change that one more time. There you go. 0, 5, 10, 15, and 20. I see a hand go up. Go ahead, Andy.
I was just wondering what difference does it make if the middle is inside the loop or not?
One more time.
So I was wondering what difference does it make if the middle variable is inside the loop inside the while loop?
So if the middle is not inside of the while loop, it's not being consistently reassigned, right? We need this block of code to run all over again to reassign what the middle is. And essentially, if we take it
Okay.
outside of the while loop, the middle will always stay at 10, regardless of how the left and right move, right? So the middle would always be pointing at 10. So by placing it inside of the while loop, that's how we ensure that the mathematical function works, where we add the left and the right together, and then floor division by 2 to get equal to that index that's pointing to 15. Does that answer your question, Andy?
Yes, it makes sense. Thank you.
Awesome.
Also, the list has to be ordered for this to work, correct?
Not there yet, but yes, that is correct. All right. Awesome. So now here's our range of list. What we're going to be looking for here is going to be the number 15. And for now, let's go ahead and print our binary search return. That is going to be taking the input list and our target. Now, when we iterate through this, we get a return of the number 3, which is exactly what we expected. We go through the 0 index, the 1 index, the 2 index, and the 3 index, which returns 15. If we print IDX, which looks like it's doing the trick of printing IDX, Uh,
You're not calling on linear search.
Oh, this is calling binary search. Thank you so much. All right, so there we can see that it's iterating through it. We get 0, 1, 2, 3, and then 3 to be able to get our second to last element. Now, if we go into our binary search and we try to apply this logic, let's go ahead and print our iteration. Let's say iteration be equal to 0. And just simply print iteration. And then we'll go ahead and increment iteration by 1. So now we're going to go ahead and put linear search against our binary search and see what that looks like. All right. So our linear search iterates through at 0, 1, 2, and 3, and then returns the index of 3. And our binary search iterates 0 and 1 times. So we can see there how it cut it in half. If we take a look at our regular linear search, what it did is essentially it iterated 1 at a time, where it checked 1. 1 wasn't the answer. So it came down, iterated again. 5 wasn't the answer. Came down, iterated again. 10 wasn't the answer. And then finally found 15 being the answer that we're looking for. Now, if we were to take a look at our binary search approach, our binary search determined our left and our right, and finally a middle. Said, hey, the middle is less than the target that we're looking for. So we're just going to go ahead and take a look at the right-hand side. When it took a look at the right-hand side, it determined that the left is 1. The middle is now 15. And then it was able to return our answer of 15. So the iteration on the right-hand side is of linear search, and the iteration on the left-hand side is of binary search. So there's a simple code to be able to write both of these algorithms, right? Our linear search we wrote up above, which is just a for index loop. And then our binary search is a while loop that is comparing our left and rights to determine 1 iteration at a time how much we should cut the list in half by. All right, go ahead, timer.
So here, when you're doing those conditionals and you're checking if or middle is greater than or less than the target, how come you're not doing like you're not assigning right to be like middle -1 or left to be middle +1?
Interesting. So that could determine something like missing values if I do something like that. So if I were to do something like middle -1 or middle +1, what that would return would be where, let's go ahead and say that it runs the logic here and it checks, hey, is this less than our target? And we did something like left is middle +1. Then that would mean that 15 is now our target, or excuse me, is now our left. Our right side is our 20. And 1 through 10 is now missing. Now, when we do the floor division, it would still return 15 to determine our middle because there's only 2 indexes that's being placed in there. When you're looking at a larger amount of data and you're doing something like +1 or -1, you're running the risk of accidentally skipping a value, which is not necessarily something that you want to do. Although it could prove to be a little bit more efficient, you are running that risk of missing a value.
But don't you also run a risk of an infinite loop if you don't increment the middle or decrement? Like in the case of if you had a I'll come up with an example. Come back
Yeah,
to you.
I'll tell you what, if you give me an example, we'll try it out.
All right.
All right, Andy?
Is this similar to the two-pointer system that Ty was using yesterday?
Kind of, right? We are still similarly using a left and a right, so we do have some sort of two-pointer. But in this case, we also have a third point, where the third point is the middle. This is not necessarily similar to a two-pointer because a two-pointer is comparing 2 points to one another, or utilizing logic upon 2 different points. Where here we have logic upon 3 different points, right? And we are searching for one independent object. We're not searching for 2 possible results, which is more of a double pointer kind of logic. Does that answer your answer? Does that answer your question there, Andy?
Yes, thank you.
All right, Cody.
I have 2 questions actually. One hops off a timer. You said you have the potential of missing the target by incrementing or decrementing the middle, but aren't we already checking that's the first condition? If middle is the target, return it. So like if it's already not the middle, increment and decrement like wouldn't skip the value that we need.
So in the example where you're skipping by 1, middle is never 15 in this case. Left becomes 15 at some point, right? But we never compare left to target. You'd have to add something about checking the endpoints each iteration as well.
I see what you mean. Okay, let me go ahead and try it out. Let's see if what happens if we can add this -1 and add this +1 into our logic and see what that returns. All right, so nothing necessarily broke within our code. We are still returning that 0 or 1. And I get what you mean because we are already checking the middle of the target. So what would be the point of keeping that as our left index rather than just cutting it that extra index outside of our list? That's a very good point to point out there, Cody. Thank you so much for bringing that up. And I guess that answers Timer's question.
Can you
Go
can you
ahead,
make
Nick.
the list instead of an even number or an odd number, can you make it an even number of elements?
Yeah,
And what if the number you were looking for was 20? Would you ever actually find 20?
absolutely. Let's check it out. All right, so in the original value, we found 20 within 15 iterations, and then we return 20. Oh, I don't know if that's correct here.
I think it targets 15.
Oh, that will do it. If my target was 20. Oh, so there you go. It didn't return 20 because we were adding and subtracting, which is, I
Well,
think,
The list is only up to 19 right now.
yeah, non-inclusive.
Thank you so much. Little syntax errors. We'll try that one more time. All right, so 20 was found within 20 steps, and 20 was found within 4 steps in our binary search. So yeah, it still finds it even if we increment or decrement.
So could you, because I think the issue would really come if it's an odd numbered list, right? So can we go back to the original list, which is a 0 to, I think it was listed out to 15, right? or whatever it was. Or I guess 16 because no. What was the original list that was giving us 20 at the end?
5 and 5.
Okay, yeah.
Uh-huh.
So I think if we're looking, because that'll give us how many list items? Five, right? That'll give us five list items. So I'm just trying to make sense. And like, I guess if we're looking at the example on the right, if we're doing that plus one, that middle, whenever it reassigns middle on that one, since 15 is less than 20.
All right, so here we see 0, 5, 10, 15, and 20. Our target is 20. We were able to find 20 in the original search within 4 different steps, and we were able to find 20 in our binary search within 2 separate steps to return our index.
I might have to draw it out later.
All right,
In my head, I feel like it wouldn't ever reassign middle to equal that last index, but I'll have to draw it out later.
let me check it out here. So here we have our code where we have our left and right. We also have our middle. We said, hey, in this case, what we're looking for is 20. We go through and we determine list middle is less than the target. That means the left-hand side is going to be middle plus 1. So the next thing that we'll be iterating through is going to be 15 by 20. Now 15 by 20 comes down. And when we do 15 by 20, we have our right-hand side, which is pointing at 20. We have our left-hand side, which is pointing at 15 because we're doing floor division. So we did the 0 iteration, which is right here. We did the 1 iteration now, which is 15 and 20. Again, we determined, hey, our middle is actually less than the target. So what we're going to do is we're going to move our left to middle plus 1. And the very last thing we return is an instance where right is 20, left is 20, and also our middle is aiming at 20, right? Because we have left is less than or equal to. And that is our
Gotcha.
second iteration there. And that's how we return the index of 4.
Okay. All right. Yeah, that makes it a lot clearer. Thank you.
Of course. All right, Cody.
It's probably dumb, but I'm wondering if it's even worthwhile instead of iterating through your while loop, is it worth just checking if the first or last index is your target? Is that any way faster?
Well, by assumption, we would want to assume that what we're working through is going to be the worst scenario possible. The worst scenario for a binary search is going to be the second to last index. And that's where binary search comes into play. You don't want to build your algorithms, especially searching algorithms, with the assumption that you know the location of where things could be placed as far as results. So that's the thing to take into consideration there, Cody. And maybe I misunderstood your question.
I was saying like for instance, two if statements. If list index start equals target, and if index list index like the square brackets of end, because that's the whole length minus one, give you, or you know what I'm saying? Get the very last index in the first. If it's equal to the target, then you ain't even got to start the while loop. I just wonder if that's worth doing before you jump into the loop, because your target could be at the very first item in the list or the very last, and you don't even need to loop through it.
I see. You just knock it out of the way right before you
Yeah,
loop.
yeah,
It might
yeah.
be worth it. The binary search the usual complex like syntax is going to be something like this. Um, I don't want to say that it is worth it, and I also don't want to say that it is not worth it because I think that's more of a situation dependent or more of a what if kind of situation. So I'm gonna go with it kind of depends. All right, Alex.
So if we had the iteration as how you had it before, where left equals middle, like without the plus one, and that elif, would it be infinite there if we tried to find the 20? Because I think that's
The catch.
yeah, I think that's what they were trying to,
Hint at.
yeah.
Right. So there we have 25. We can see the list is returning 20, and that's what we're looking for is 20. Let's go ahead and run this.
Yeah.
Got it. So without incrementing or decrementing there, we could run into an infinite loop if we are looking for the final index. Awesome. Thank you so much.
Yeah, I was just about to give you an example for that infinite loop too.
All right.
Is it if it isn't available, it'll loop forever? The target?
So if you don't increment or decrement it, then left will be at 15, right will be at 20. And then if you add those and then take the division, then it'll put center at 15. So center will never get to 20.
There you go. Yeah, so just like Alex said, without incrementing or decrementing, we'll never touch those final indexes, whether it be on the furthest left-hand side or on the furthest right-hand side. Thanks so much, Alex, for pointing that out. All right. Any other questions?
What if your target isn't in the list?
Yeah, so if my target is not in the list, let's go ahead and pass something like
19?
45.
Sure. It doesn't matter actually, right?
Yeah, it would still return -1. So once it's done iterating through the list and it determines, hey, this is the last index that I'm checking for, and it's still not matching, then it would break out of our while loop because our left is no longer less than or equal to the right side, and it would return our -1. All right, something important to bring up that Nick had mentioned. In this example that we're working with, we are working with numbers that are in ordered. And our binary search would only work, again, binary search only works with ordered data structures. Let me go ahead and emphasize that. So only works with ordered iterable data. Important to make sure that we annotate and maintain throughout our program. It only works with ordered iterable data. All right, if we were to pass in something that is unordered, let's go ahead and say that we have a list that works as such. Say we have 0, we have 20, and then we have 15. And then finally we have 10 and 5. And let's change this back to 20. Now, will our linear search still work in this case? Yeah, linear search would still work just fine, right? Where we're iterating from left to right and checking one index at a time. But our binary search would actually crash because it would no longer be able to run the logic of determining if our middle is larger than the target or less than the target. And they would eventually return, more than likely, something like -1. In this case, it returns 0, 1, 2, and it returns the index of 4. 20 is actually located at index of 1. So I don't even know why it's returning the
You're still, I think you're still checking the input list, aren't you, instead of the unordered?
Da-da-da. Yes, I am. All right, so there we can see the -1 happening. While in our regular linear search, we can get an output of 1. All right, go ahead, Alex.
I found another correction for the binary search loop, but if this is not the time, then we can come
Oh,
back to it.
send it. Let's hear it.
So with right equals middle -1, you can still miss some correct answers. So if the list was 0, 1, 2, 3, 4, 5, and you wanted to find 1, then you would skip over it because the center would be pointed at 2 at the beginning because it's 5 divided by 2. And then after that, it would set right to be center -1, which would be 1.
Uh-huh.
And then 1 divided by 2 would be 0. And then it would just skip over 1 because center would never be 1.
All right, so let me run this. So it looks like when I execute it, just to make sure that I'm tracking correctly, you said if the input was 0, 1, 2, 3, 4, right? And I was searching for the
With
number.
a 5 as well.
Oh, okay. Let me go ahead and change that.
Starting at 0, starting at 1.
Starting at 0.
Okay. And we're saying that if we're looking for the number 1, it would return false. So we start iterating through 0, 1. It finds the index and returns 1.
Mm-hmm.
In binary search, we do the first iteration. It does the comparison. It says, oh, okay. Well, the middle, which in this case would be the number 2, is greater than the target. Then it would say right is equal to middle -1. So now we would have 0 and 1. Right? And then it runs it again. So is 0 less than or equal to the number 1? Well, that's correct. It does the floor division. So now we're looking at the iteration of 0 for iteration 1 there. So list at index 0 returns or is not equal to the target. It's less than. So when it says left is middle +1. Left
So
and right is the number 1. And we finally get a return value of 1.
so it goes back. I see. All
Awesome.
right. Thank you.
Of course. All right. Any other questions regarding binary search? And thank you so much for this minus and plus one. That completely would have flown over my head if I didn't get that raised to my attention. All right, perfect. If there aren't any other questions, let me go ahead and pause our recording here.